So we have our next topic with exponentials. If you've had an algebra class or even a pre-calc class before, you probably know what's following. If not, that's okay. We're presenting it as if it's brand new, okay? So here's our motivating question. This is the one we're going to answer by the time we can develop all of this theory around logarithmic functions, okay? So how long does it take $800 in an account earning 5% interest compounded continuously to grow to $1,000? $1,000. Okay, so it seems like a pretty pertinent question. You've got, you know, you want $1,000. You know you can get this interest rate. You're compounded continuously, which is usually the best kind if you're the one investing, and you have this principal starting value of 800. Okay, so this is all indicating, again, because of this continuously compounded, not in semi-annual or quarterly or monthly, that is telling you we're using PERT formula. All right, and then we can start plugging in what we know, okay? $800, that's your initial amount, okay? So this is your P. And then you want it to end at, this is your accrued amount, $1,000. Change percent to a decimal, and that's your R, okay? So I'm gonna start plugging in what we know. 1,000 equals 800e to the 0.05, again, percent to decimal, times t. Okay, if I want to answer the question how long, I need to solve for t, so that's my goal. All right, so when you encounter a word problem, this is a nice way to kind of diagnose what's going on. It's almost like diagramming a sentence or something. You know, you're picking out the information you know, and then you're trying to figure out, what do I not know? And usually words like how long or something like that would indicate some sort of time value. Okay, so what can I do to start solving for t? All right, so t is buried in an exponent here. Well, if I'm solving for t, I want to start undoing the outermost layer, which is this 800. So I'm going to undo 800, and I'm undoing the operation of multiplication, right? If it's not written, this 800 is multiplied by e to the stuff. So I'm going to divide both sides by 800. Okay, 800's cancel over here. Here I can cancel some zeros. 10/8 reduces to 5/4. You can leave it as 1,000 over 800. You can change it to a decimal, but here's the equivalent fraction. Okay, again, if I'm trying to isolate t, I need to start peeling away the outermost layers, right? So I can get to the interior t part. Now I'm at a point where I need to undo e, okay? So how do we undo e? Okay, so let me elaborate on that a little bit. We undid multiplication with division. I would undo addition with subtraction. I would undo a square with a square root. This is really asking, how do I undo exponentiation? Right? We talk about exponential functions. How do I undo something that's up in an exponent? Okay, well, this idea of undo was in a previous video, and undoing is really just by using the inverse function. The inverse of addition is subtraction. The inverse of multiplication is division. So I need an inverse for exponentiation. Okay, so here's what we're going to start with. I don't know the inverse right now. You know, maybe you've already seen this and you've encountered it and you can guess, that's fine. But again, let's say we're starting from scratch and this is not familiar with you. So we define the following function, and this function will undo not just the e, but in fact any exponential function. So I'm not going to have e's in this next line, I'm going to replace them with a's. Okay, so if we encounter this type of equation, x equals a to the y, we're going to define this as the following. Y equals the log with a base A. So that is a subscript A of x. Okay, so this idea of a log is this brand new function that's actually going to undo the exponents. Here's why, okay? These y's are the same thing, they're just in different places. So what is occurring here is we have solved for the exponent. Which is exactly what we need to do to get to t, right? If I want to get t by itself, I need to somehow solve for the exponent. That's what this definition does for us, okay? If this line looks confusing, okay, let me just try to offer an analogy, okay? These mean the same thing, okay? So pretend we're learning a new language. Maybe we're learning French. And we understand English pretty well, okay? We feel pretty good about exponents and how to manipulate them. We've studied our rules. We've passed our web assign. We feel good in English, okay? But now we've got to start working on French, okay? So these have the same meaning, but just in different languages. This is English, this is French. So my analogy is this is the exponent language, this is the logarithm language, but they're saying the same thing, okay? So before we get back to this problem, I'm actually going to pause. I'm going to say, okay, we will return to this problem at the end. So this 5/4 equals e to the stuff. We will solve this after we've kind of understood and had some time to practice with this definition, okay? So we have our motivating question. We know we're going to return to it. But before we jump right into solving word problems, let's get a good understanding for this particular logarithm function. So, as an example, we want to use the definition to find the number. Okay, so here are some logarithm problems that should simplify to a number. I'm going to write them all down first and then we'll kind of talk them out. All right, so my base is 2. I'm taking the log base 2 of 1. My base is 2 again, taking the log base 2 of 2. I'm going to do a whole bunch of these, okay? Log base 2 of 4, log base 2 of 16, log base 2 of a half, log base 2 of the square root of 2, log base 2 of 0, and log base 2 of -1. Okay. These are all numbers. Okay. These are not algebra. I'm not trying to find an equation answer. These are just numbers. I have to find out what number is this. Okay. So in order to do that, I'm going to use the definition of the logarithm. Okay. Again, I'm going to translate. Thinking about, okay, this is French and I don't understand French very well. Let me think about it after I translate it over to English, okay? So, I don't know what this number is. This number is unknown to me. Okay, so I'm going to replace it with a question mark. But now I have an equation that's set up like the following. Log A is 2. I'm taking the log of 1. X is 1. So I can go ahead and plug in what I know. A is 2, X is 1. As I translate this over to an exponential, okay? So what I'm asking for here is what number will give 1 when I take 2 to that power, okay? So 2 to what power is 1? Again, if we know our exponent rules, if we feel comfortable with the exponents, we should know 2 to the 0 is 1. So 0 is the number we're searching for. So if I translate it over to exponents, hopefully I have a better understanding. This one I'm going to do a little bit quicker, okay? Again, I don't know what this is. Let me translate it over to the exponent. A is 2, X is 2. I'm trying to figure out y. So if I write this as an exponential, here's my exponential. This is my translated work. 2 to what power is 2? Oh, well, 2 to the first power is 2. So my number is 1. Again, let me box the answer. The answer is the number I'm calculating here. This one, if I rewrite as an exponential, is 2 to some power is 4. But what power of 2 gives you 4? 2 squared gives you 4, Write the answer over here where I have more room. 2 is the number I'm looking for. Maybe this one I just talk out. I don't read, okay? This is asking 2 to what power is 16? So what exponent on 2 is 16? There's 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16. The power I want is 4, okay? Same thing here, but I will write this one out. This one's asking 2 to some power is a half. What is that power? So we really got to know our exponent rules. What kind of exponent gives you a fraction? A negative exponent. Because this is 2 to the 1st in the denominator, my exponent is a negative 1. That's the number for this logarithm. This one again, I will rewrite. This is saying 2 to some power is root 2. So now, again, different exponent rule. What power of 2 gives you roots? Fraction powers. Which fraction gives you the square root? A half. Okay. If you want, maybe just pause the video and try these. Okay. Give it a little pause, try on your own, see if you're right, fast forward. Okay. I'm going to continue going. 2 to some power is 0. That's this one. 2 to some power is negative 1. Okay. So what exponent on 2 gives you 0? And what exponent on 2 gives you negative 1? Okay. These are a little trickier. Let's think about what the exponential graph looked like. There it is. That's the exponential graph, y equals 2 to the x, this growth curve. Does this curve ever hit 0? No, 0 is never an output. I have an asymptote at 0. This number does not exist. Similarly, does this graph ever hit negative 1? Is there ever a negative 1 as a y value as an output? No, it has a range of 0 to infinity. It's never negative. So this one as well does not exist. Okay, so we can't always find a number, but a lot of times that number just comes from an exponent rule. Okay. With this idea, I want to look at a visual of what the logarithm graph is. Okay, I just had that exponential graph up there. Let's compare the graphs of a to the x versus log base A of x, okay? So we're going to look at some visuals, but I'm going to graph them both over here, okay? So the exponential graph looks like that, okay, right? We got this growth curve. This is if a is greater than 1, we have growth. If a is less than 1, we actually have decay, but let's just assume a is greater than 1. Now, if I want to graph the log function, okay, this is any log, right? Log base a. They are inverses, okay, right? We're undoing an exponentiation with an inverse. So if I plot some points here, okay, like I know my y-intercept is 0, 1. Well, if the y-intercept is 0, 1, the inverse graph swaps x and y and will go through the point 1, 0. So that's something I want to mention here, what my intercepts are, okay? On the a to the x curve, the one in blue, my intercept is a y-intercept of 0. So maybe I'll just write the ordered pair. And on my black graph, my log graph, which I don't know what it is yet, I just have this 1 point, the intercept is 1, 0. Okay. What else can we exploit when we talk about inverses? We can also talk about asymptotes. Okay, the asymptote of a blue graph is horizontal. It's approaching y equals 0. So it's a horizontal asymptote of y equals 0. Well, again, inverses swap x and y. So the log graph is going to have a vertical asymptote of x equals 0. Okay, so I can kind of picture what that is, right? It's going to approach this vertical line right here. It's got to go through my intercept dots. Okay. All right, what else? Maybe I talk domain and range as well. So the domain of the blue graph, my exponential graph, is negative infinity to infinity. Its range, again, if we think about like squishing it into the y-axis, is 0 to infinity. Don't include 0. So the inverse graph is going to swap both of those. The x's and y's are switching. So the domain is 0 to infinity, but the range is negative infinity to infinity. Okay. So I'm going to get something that looks like this, where if I squish this into the y-axis, everything gets covered, but if I push it into the x-axis, only the positive x's get covered. And I also, if you remember talking about inverses, we have this nice symmetry, that if I could literally fold the board over this dashed line, or if I folded the board over the dashed line, the blue and the black graph should lie on top of one another. They are symmetric about the line y equals x. So this is the curve of a log function. And the blue is the curve of his inverse, an exponential. Okay? I'm going to solve one equation and then we'll return to the problem that we had at the beginning of the video. Let's see. Okay. We want to solve something with algebra. Log base 4 of the quantity 5 plus x equals 3. Again, this 4 is a subscript. It's with the logarithm. It's not being multiplied or anything. It's telling me what my base is. Okay, so I need to interpret this as an exponential. All right, I can't get to the x right now. It's buried inside of parentheses that I'm then taking the log of. So I'm going to translate this to an exponential. So I'm going to use the definition that I just erased. So hopefully you got it in your notes and you can recall it or just rewind the video. Use the definition to rewrite as an exponential. Okay, so think about what's going where. Where's the a, where's the x, where's the y? Okay, this 4 represents the base. Logarithms solve for the power. So this 3 is the exponent. And then what I'm taking the logarithm of is what is isolated in the exponential function. So I have this 4 cubed equals 5 plus x. I can solve that. 4 cubed is 64. 64 is 5 plus x. Undo the 5, and I get that x is 59. Okay, so that's how you would solve a logarithm of this type. You want to rewrite it as an exponential. Okay. All right, so we have enough for if we could solve this logarithm, maybe we can go back and actually solve the exponential that we had at the beginning, which was 5/4 equals e to the 0.05 t. Okay, kind of like the last problem, I'm stuck right here. Well, when you feel stuck, rewrite or translate it to a log. Okay, so thinking about that definition, if you don't have that definition anymore, make sure it's written down. If you have nothing else from the video,